So, hi, and welcome to this first lecture in a mini course called Dualities and Spacetime in String Theory. My name is Keizo Matsubara, and I will present these two lectures. And I will present basically some background on dualities and string theory. And another important issue to discuss is how these dualities should be interpreted. And there will be a special focus on how to think about space-time and the concept of space-time as it arises in string theory. I would also like to acknowledge that the presentation I'm doing here is based on previous work that I've done with Lars-Göran Johansson and with Chris Smenk, so I would like to bring that out so and credit their contribution to the kind of work I'm presenting here. So I will mention different ways of thinking about dualities, but the focus will be on an account that I myself support. And you should feel free, and I encourage you to look at other discussions and accounts about dualities in the philosophy literature, and of course also in the physics literature. So in this first lecture, I will give some background information on string theory. And it would be ideal if you already knew a little bit of string theory to follow this. There is a planned other mini course that will introduce a bit of string theory for philosophers. So if you can find that, and if that has been produced, it hasn't been yet when I'm recording this, I suggest that you find this on the same webpage. So in this first lecture, besides this background on string theory, I will talk a little bit about what dualities are and present some examples. And then I kind of explain what the problem interpretation is and why they kind of lead to questions and problems of interpretation. And then in the following lecture, I'll actually try to address and attempt to answer these problems of interpretation. And also discuss more about how we should think about space-time in string theory and question some of the common sayings or ideas that about space-time in string theory. But that is for the following lecture. So a little bit of motivation. String theory has been one of the most popular approaches towards developing a theory of quantum gravity, which is something very challenging in trying to reconcile what we've learned from general relativity and quantum physics. And dualities play a very important role in string theory. And what I will mostly address are philosophical and conceptual issues regarding these dualities. There are a lot of technicalities on the physics side that I will not delve deeply into or discuss only very briefly. And as I've already said many times, in the next lecture I will go more into ideas about how to think about space-time in string theory. So there are many different kinds of string theory or types of string theories, and they are connected by a number of dualities. And there are 5 superstring theories called type 1, type 2a, type 2b, and E8 cross E8 heterotic, and SO32 heterotic. You don't have to understand what that exactly means right now, but there are different versions of string theory, and they are connected by the kind of dualities we're discussing. They're also connected to 11-dimensional supergravity in another limit, and it's generally believed by physicists that underlying this kind of web of dualities, there is some kind of M theory or something that is called M theory. And it's not really decided what M stands for. It's a theory we don't really understand. And the reason why it has that kind of weird name, M, is that originally a number of ideas were thrown out, like membrane theory or matrix theory. They had it in common that they all started with M. So in that sense, that's why the name stuck. Kind of M theory, but we don't fully understand this theory. But the idea, according to physicists, is that there is this underlying theory, and the other different string theories and the 11-dimensional limits are all kind of different limits of this underlying theory. And this kind of understanding arose, say, in the middle of the 90s, where this picture was kind of developed. And what are dualities then? I've talked about it many times, and I've just mentioned the name, but to give some kind of initial formulations, we have two theories, and they are apparently distinct. They might describe, for instance, string propagating in different backgrounds. Yet they have, in a sense that will be a little bit more articulated in later on, the same physics. And I'll read two quotations. The first one from a book by Zwiebach. Duality symmetries are some of the most interesting symmetries in physics. The term duality is generally used by physicists to refer to the relationship between two systems that have very different descriptions but identical physics. There is something slightly peculiar between this quotation, because should he really say two systems with identical physics, or is it rather one system with different descriptions? And I think it's rather the second option that makes more sense, but we will come back to that. Another quotation from another book, a very technical book co-authored by a number of authors, is as following. In quantum field theory, that's not the same thing as string theory, but we can still apply it here, two or more descriptions of the same theory, or in some cases a symmetry of a quantum theory, which is not usually a symmetry of any classical limit. So these kind of hints a little bit towards what dualities are and how we should perhaps understand them or think about them. Okay. I would also like to mention that, of course, the term duality is used in many different ways in physics and mathematics. And you should not assume that just because you hear the word or the term duality used that the account I give now applies. These are a specific kind of dualities that I'm interested in. It should also be mentioned that some instances that are called dualities are formally very similar to the case I'm discussing here. The difference, though, is that the dual pictures are empirically distinguishable, because even though you have a formal similarity, the things that are identified by the duality mapping are given different empirical interpretations, or it could be the cases where aspects that are not empirically accessible in the dualities I'm talking about are given some kind of external interpretation, and then we have a different situations. So when I talk about dualities here, I presuppose that they are exact, and I furthermore assume that the dual pictures are empirically equivalent. So I'm restricting to this subcase. There are many other dualities that, as I said, are kind of closely connected to this, but differ in this respect. So from now on, when I discuss dualities, assume that the dualities are exact, assume that they are empirically equivalent descriptions, unless I say something different. And as I said, string theory is one approach to quantum gravity, and it also tries to describe all interactions within one unified framework. And the basic assumption is to replace point-like particles by one-dimensional extended strings. Strings can be open, having endpoints, or closed, forming little circles. And different vibrational patterns of the strings would correspond to different particles. The standard analogy used is to say that different particles are different tones or musical notes of the string in some sense. And the idea is that all the different particles, describing all the other kinds of interactions we're familiar with, should be able to be reproduced within this framework. And also gravitons, the quanta describing gravitations, are also captured in this framework. We always get gravitons from string theory. When an ordinary particle moves throughout space-time, it tracks out a so-called world line, and given that a string is a one-dimensional object, when it moves through space-time, it gives a two-dimensional world sheet, analogous to the world line that a particle would do. And that is a two-dimensional manifold. And when this is described at the classical level, we think of the world sheet embedded into a target space, which is at least originally thought of as space-time. And at the classical level, there is not much problem of having that picture, actually. And this, of course, you have actions, you have equations of motions and things that can be derived at the classical level. And this is kind of a sigma model. But of course, what we're interested in is not a classical theories of strings moving in a space-time. What we're interested in is actually the quantum versions of string theory. And a lot of kind of peculiarities happen when we try to quantize the theory. For a bosonic string theory, which only has bosons, the target space that the world sheet's supposed to kind of be moving in has to be 26-dimensional. There are some other problems that are not quite resolved with that theory. And of course, a purely bosonic theory would not be able to capture or describe the fermions that we know exist in our world. So regardless, the 26-dimensional bosonic theory is not realistic in the sense of being a candidate of describing the world we live in. So instead, what people have tried to develop are superstrings. And in that situation, the target space have to be 10-dimensional instead. So we have a 10-dimensional target space. And of course, since in the classical picture, the target space was introduced to represent space-time, and of course, this is generally taken to say that, okay, then superstring theory requires space-time to be 10-dimensional. That's the standard way of explaining, of describing this. And I'll put this slightly into question, even though not fully into question in all details, but I'll describe the situation to be a little bit more subtle than this. There are different kinds of dualities in string theory, and my focus will be on target space dualities. These are dualities identifying different target spaces. So what differs from one dual description to another is what the target space is. And this will be my focus because I'm addressing issues about space-time and spatiotemporality, and this is kind of most relevant for that. It should be mentioned as well that there are S-dualities in string theory, and there are counterparts of these in different quantum field theories as well. And in S-dualities, it's not so much the space-time, it's rather the entities and the description of the entities that differ from one picture to another. More specifically, the difference is what entities are considered to be the fundamental entities, and what are kind of more, in a loose sense, kind of more extended or composite or non-fundamental entities. So in one picture, the kind of exchange place. And I will not talk much about this, because this is more about the ontology of the matter and the entities, and I would like to focus in this talk more on the question of space-time. There's also a lot of things written on the so-called ADS-CFT or gauge gravity dualities. There are a number of different versions. What's interesting with that is that they relate string theories to quantum field theories of a certain kind, but they are defined in different number of dimensions. So these examples are actually also rather interesting for questions about space-time, but I will not address them in these lectures. Maybe I'll say some words, but we'll see. So what I will first look at is examples of closed strings on a 10-dimensional manifold where one of the dimensions is compactified to form a circle. So here I'm talking about the target space. The target space is such that you have 9 large dimensions and one forming a circle. And given that this circle, we get quantization conditions, and this would be the same for particles as well. Basically, the standard quantum mechanics in a compact or space would lead to certain quantization conditions. But for strings, we also have another factor, which is that the strings can be wound around this compact dimension a number of times. And it turns out that the mass spectrum for the strings, for now ignoring the vibrational states, is composed both of factors due to the basic quantization conditions that would be the same as for particles, but also for these kind of winding states. And the duality here is such that if you exchange the radius, so the original radius r is replaced by the string length squared divided by r, we can call that r tilde, and also at the same time switch the momentum states and the winding number, then we get the same mass spectrum. Okay, and it should be noted that this is only a starting point. So what happens in the full quantum version of the theory? It turns out that once we quantize them, they are theoretically equivalent. We have isomorphic Hilbert spaces, we have equivalent partition functions and scattering amplitudes and all that. They agree on everything which we think of as physical. And it will also turn out that it might not be completely obvious, but they're also kind of empirically indistinguishable. So even though we have kind of thrown in a large radius or a small radius, we cannot really detect this difference. Exactly what that will lead to, or what we will actually detect, is something I will discuss more in the following lecture. Note, though, that when I say everything physical, that means everything that is in principle observational. It doesn't mean that is what is currently observational with what we can now directly observe with current technology or something like along those lines. What is identified in both pictures can go very well beyond what we can currently observe, and it's not supposed to be understood as some kind of positivist or instrumentalist account, even though it perhaps goes a little bit in that direction, because there are aspects of the dual descriptions that we might not want to take to be physical, because they are not part of this kind of shared structure that is identified under the duality mapping. Okay, let's talk about mirror symmetry. And mirror symmetry are kind of a more extreme kind of target space duality, where the target spaces even had different topology. And maybe you already know what different topology means, but if you don't, I'll give an example. Spaces with different number of holes have different topologies. Basically, topological aspects are things that are preserved if you stretch and bend the things in various ways, but you're not allowed to cut or tear the things. So things that are topologically different could be something like a sphere and a donut shape. They are kind of examples of spaces with different topologies. And in the case of mirror symmetries, we have target spaces of different topologies. They don't have even the same kind of overall shape or connectedness or anything like that. So that is why this is more extreme than the case of the T duality I talked about earlier. And the mirror pairs are in the most studied case something called Calabi-Yau manifolds. And in the dual pictures that I'm thinking about here, we mostly have 4 space-time dimensions that are the same, or 4 dimensions of the target space that are the same in both pictures. But the compact dimensions form these little Calabi-Yau manifolds, and they can have different topologies. Also, when this mapping is done, typically, it's always the case that if you have a string theory of type 2a on one of the manifolds, it becomes a string theory of type 2b on the other one. So both the topology and the type of string theory is interchanged in this kind of mapping. But if one thinks of target space as just being spacetime or representing spacetime pretty straightforwardly, what then is the topology of spacetime? If we have two alternative descriptions that give the same physics and are empirically indistinguishable, can we say anything about spacetime and how we should understand these extra dimensions? So, this is just my brief presentation of these dualities, and this we're getting to the end. Summarize the dualities, different pictures of the world, and this presents us with a problem of interpretations. Should we see dualities as instances of underdetermination? No, but by assumption here, that when I say dualities, all of them are empirically equivalent. So one possible answer would be to think of these as instances of underdetermination. On the other hand, if the answer is that we shouldn't think of them as instances of underdetermination, how should we instead interpret what the dualities tell us about reality? And this ends the first lectures, and in the following lecture I will try to answer how dualities should be interpreted and deal with these questions and talk about how we should think about space-time in string theory. Thank you for listening, and I hope that you will listen to the following lecture in this little mini course.